Simple linear regression looks basic, but most of econometrics is already hiding inside it. We are going to use this one model to talk about causal interpretation, estimation, goodness of fit, and statistical precision. The point is not just to draw a line through data. The point is to understand what that line means, what assumptions justify it, and what goes wrong when those assumptions fail. The simple regression model is written as y equals beta 0 plus beta 1 times x plus u. Here is the dependent variable, x is the regressor, beta 0 is the intercept, beta 1 is the slope, and u is the error term. The slope tells us how y changes when x increases by 1 unit, holding everything else fixed. So if we write wage equals beta 0 plus beta 1 times education plus u, beta 1 is the change in wage associated with 1 more year of schooling, holding the omitted factors in u fixed. That takes us to the most important condition in the model, the zero conditional mean assumption, written as E of u given x equals 0. Once we know x, the average value of the error term should still be 0. In plain language, the omitted influences inside u should not systematically move with x. If they do, beta 1 starts picking up more than the effect of x itself. Suppose ability affects wages and is positively correlated with education. Then a regression of wages on education alone will overstate the return to schooling, because education is partly standing in for ability. How do we estimate the line? Ordinary least squares chooses beta 0 hat and beta 1 hat to minimize the sum of squared residuals. A residual is the difference between the observed y value and the fitted value from the line. When you solve the first order conditions, you get two famous formulas. Beta 1 hat equals the sample covariance between x and y divided by the sample variance of x. Beta 0 hat equals y bar minus beta 1 hat times x bar. Those formulas show the slope is driven by co-movement. If x and y move together positively, the slope is positive. If they move in opposite directions, the slope is negative. It is also important to separate the population regression function from the sample regression function. The population regression function is the true conditional mean relationship, E of y given x. The sample regression function is the fitted line we get from one particular sample. Different samples produce different fitted lines, because the estimates vary from sample to sample. Beta 1 is the true population parameter. Beta 1 hat is the estimate from the sample in front of us, and the error term u is not the same as the residual e hat. The error term is unobserved. The residual is observed after we fit the line. Let's make that concrete with the CEO salary and return on equity example. Suppose we regress annual CEO salary on a firm's return on equity. The fitted line might look like salary hat equals 963.19 plus 18.50 times RO, where salary is measured in thousands of dollars. That means a 1 percentage point increase in return on equity is associated with about $18,500 higher predicted salary. But this is an association, not automatically a causal effect. Firms with higher return on equity may also be larger, operate in different industries, or have different compensation structures. OLS also has a few exact algebraic properties that are worth remembering. First, the residuals always sum to 0. Second, the sample covariance between x and the residuals is 0. Third, the fitted line passes through the sample means, so the point x bar, y bar lies exactly on the line. These are not probabilistic statements. They are mechanical consequences of how OLS is defined. Now let's talk about goodness of fit. Total variation in y can be decomposed into explained variation and unexplained variation. In symbols, SST equals SSE plus SSR. R squared is the fraction of total variation explained by the regression. An R squared close to 1 means the line tracks the sample data closely. An R squared close to 0 means the line explains little of the variation in y. But a high R squared does not prove causality, and a low R squared does not mean the slope estimate is useless. Functional forms matter because regression is linear in parameters, not necessarily linear in variables. In a level model, beta 1 is the change in y from a 1-unit change in x. In a log level model, Beta 1 is approximately the percentage change in y from a 1 unit increase in x. In a log-log model, beta 1 is an elasticity, so it tells us the percentage change in y from a 1% change in x. Logs often make interpretation cleaner and line up better with theory, but the estimation logic is still ordinary least squares, as long as the parameters enter linearly. So when is OLS unbiased? In the simple regression model, we usually summarize the core requirements as SLR1 through SLR4. SLR1 says the model is linear in parameters. SLR2 says we have a random sample. SLR3 says the regressor varies in the sample. And SLR4 says zero conditional mean, which is the crucial assumption for causal interpretation. If those four conditions hold, then on average beta 1 hat equals beta 1 and beta 0 hat equals beta 0. Variance and standard errors tell us about precision. The variance of beta 1 hat, conditional on the x values, equals sigma squared divided by the sum of squared deviations of x around its mean. Precision improves when the error variance is small and when the regressor has more spread. If x hardly moves, it is hard to learn the slope. Because sigma squared is unknown, we estimate it with the residual sum of squares divided by n minus 2. That gives us the standard error of beta 1 hat, which we later use for t statistics and confidence intervals. If we add one more assumption, homoskedasticity, we get the full Gauss-Markov setup for simple regression. SLR5 says the variance of the error term is constant across values of x. Under SLR1 through SLR5, OLS is not just unbiased, it is also the best linear unbiased estimator. The first four assumptions deliver unbiasedness. The fifth gives us the standard variance formulas and the efficiency result. That is the core logic of simple linear regression. We started with the model, derived the OLS estimator, separated population from sample objects, looked at goodness of fit, and saw why the assumptions matter so much. The next step is inference. Once we have an estimate, how do we judge whether it is precise, statistically significant, or economically meaningful? That is where we go next.